Okay, so we can start. So last time in the last class we were doing, so we went to a stochastic case and we defined interpolation constants which are, so just to remind, so this is definition 4.13, and here we define this delta star f, which is infimum of f minus 1 over n, sum of infimum of fi, I equal 1 to n. So this we call it a function noise, and we proved few results on this lemma 4.15, and here we have delta star f is greater than or equal to 0, and this is and then second one is interpolation holds, if and only if delta star f equals to 0. Okay, and by interpolation we mean that they all share the same x star. Okay, so if fi share all the, if infimum of fi is achieved at x star for all I, then obviously if I take a sum, then that will be f as well. Okay, so that, I mean, we have already proved this. So interpolation happens if and only if del star f is equal to 0. And then we defined something called gradient noise. This is 4.16, and here we assume L max smooth. So basically, if fi's are Li smooth, then the sum, okay, which is f will become L max smooth, because I will take the max of all Li and then it becomes L max smooth. We can also say L average smooth, so that's fine. And then we prove that the first thing is, the first thing we define is the gradient noise, right? So the first thing is the gradient noise, which is sigma so definition 4.16, and this is where we define sigma star f is infimum over x star in arg min of variance of grad fi x star. Okay, and this we call it gradient noise. And then we had this lemma 4.17. So all this setup is being done to study stochastic gradient descent. Okay, so we had one variant of the proof. We will do another cleaner variant today. So in this, for the gradient noise, we have sigma star f is greater than or equal to 0. The fact that it's a variance, so the first argument is trivial, and if we have sum of convex, so meaning these fi's are convex, then in that case sigma star f is variance of grad fi x star for all x star in arg min of f. So if we have a sum of convex, then sigma star f is variance of grad fi x star, and x star is the minimizer of f, and x star is not necessarily minimizer of fi. Okay, so x star is a minimizer of f, but we are not assuming that x star is a minimizer of fi. But what we are trying to say is, like, how are the gradients varying? Because for this x star, I know for sure that grad f x star will be 0, because x star is the minimizer, so this does imply that. But what I don't know is what about the behavior of the Fi's on X star. Okay, so how much they vary, right? If this is 0, then X star will interpolate all of the Fi, because Fi's are convex. So by interpolate I mean that Xi, obviously if these are 0, then X star is a minimizer of all Fi, right? But that's a very special case where X star is a minimizer of F, but then we want to see what about the variations of Fi on that X star. Okay, so it may not be 0. Okay, so if it's 0, then it interpolates, right? So we have seen this. So that's what I said. So if interpolation holds, then sigma star F will be 0. So if interpolation holds, then sigma star F is 0. And if I mean, here I don't even assume that the Fi's are convex, but it's if and only if now, then if Fi's are also convex. Okay, because if Fi's are convex, then, and if interpolation holds, then if sigma star F is 0, then interpolation holds. So we can also say the other case. So this becomes an equivalence if sum of convex. So this becomes equivalence if we have sum of convex, or meaning that is Fi is convex. Okay, remember F was sum of these Fi's. Okay, we are looking into this special case of functions throughout, right? This is what we see in machine learning, right? Sum of Fi's. So that's, we are specific in this setup right now, and also a stochastic variant. So we have done this proof, and then we will today do the stochastic gradient proof. So this will be our second proof. The first proof was not very easy. Okay, so this will be very clear. Okay, so lemma 4.18. So we need these lemma for the proof. So let us assume sum of L max smooth. Okay, so we have this setup. The proof that we did before may not have assumed this. Okay, so what we will do will be for the sum of smooth functions. Yeah, so yeah, if for sum of L max smooth we have sigma star F is less than equal to 2 L max of the delta star F. So that's the first result, and second result is moreover if Fi is mu strongly convex, then 2 mu delta star F is less than equal to sigma star F. Okay, so this is how these delta and sigma are related. Okay, so let us try to prove this. So let X star be the argmin of F. Now using lemma 2.28. Okay, so the lemma 2.28 was, I will write this here. So if F is L smooth and lambda greater than 0 and infimum of F is greater than minus infinity, then for all x rd, we have 1 by 2l norm of grad fx whole squared is less than or equal to fx minus infimum of f. So we have proved this lemma before. Okay, so with this lemma we can write. So with this lemma we can write the so we can write norm of grad fix whole squared is less than or equal to 2l max of fi x star minus infimum of fi. So these fi's are also L max. These fi's are L max smooth, so I can use that L here as L max. So using that lemma, I have applied these on fi. Okay, so this 2L goes there. So in place of L, I have L max, because fi's are also L max smooth, right? So okay, so and this is for all I. We can say that L max is the max for all Li. So the conclusion then will follow after we take the expectation. Okay, so and what we are looking for is the relationship between sigma star f, which looks like this, and delta star f, which looks like this. So we are supposed to show sigma star f is less than or equal to 2L max delta star f. So delta star f seems to be the right hand side, which is of the form fx star minus infimum of fi. Okay, so so if we take the expectation, then we want to know whether the expectation of the left hand side will be sigma star f. So this is defined to be variance of grad fi x star. Okay, so and I'm missing a star here, right, because we applied this on star. So if we take expectation, so taking expectation, then we have expectation of norm of grad fi x star less than or equal to 2 max, and then expectation of fi x star minus infimum fi. So sigma star f, we are thinking of sigma star f. In fact, what we have seems to be the other way around. So what we have, sigma star f is on the right. Okay, so it should be the left hand side should be variance. So I think I have done some calculation here. Sigma star f is this. Okay. So what we can do is that let us start with sigma star f, and with sigma star f we have this, and we will expand the variance formula. Then we will have expectation of this minus expectation of this whole squared, and the expectation of this will be the f itself. So that will vanish because x star is in the minima of f. Then you will be left with just grad fi expectation of grad f I star like that, and then we will have the upper bound like that to L max, and then we will get the final thing. So yeah, let us do it here. Okay, so let us start with sigma f star. Okay, so sigma f star, and this we know is a infimum of infimum over all x star, and which is coming from argmin of f. So this is an infimum over all x star, which is a minimizer of f. Okay, so if I don't take the infimum, then sigma star will be less than or equal to the x star, because this x star that we have chosen is some one of them. Okay, so hence if I pick instantiate by just one of them, then sigma star is going to be less than equal to this. So I can directly say that this is less than equal to this, because I am removing the infima. So this will be less than equal to v of grad f I x star. Okay, and then we will apply the variance formula, right? So variance of x is expectation of x minus expectation of x whole squared, right? So in this case, we will just expand the variance formula. So we can just write it here. So this will be expectation of in the sigma. Okay, there is no norm involved here. Okay, but what we need is a norm, right? Here, here we don't see any norm. Oh yeah, but when we have the when we do the variance formula, okay, let's see. So this will be expectation of norm of gradient of fi x star minus gradient of, so x minus expectation of x whole squared, and then I'm supposed to take the norm, right? So x in our case is this grad f xi, and then I have to take the expectation of that, but the expectation of the grad of fi will be the f itself, because the f is defined like that. Okay, so f is like the average of the fi's. So if I take the second term, so I will do that one extra step. So this is expectation of and we need a square here also, right? The variance. So this equals expectation of norm of grad fi x minus, and this becomes f x star, and then grad. Now this becomes 0 because x star, since x star is in argmin of f. So since x star is an argmin of f, obviously the gradient must vanish there. So that goes away. So eventually we are left with is expectation of squared, which we have there, and this is bounded by 2L max. Okay, yeah, so we did expectation everywhere, and so sigma star f is less than equal to 2L max is there, so we are expecting everything. Oh yeah, but expectation of fi will be infimum of f. Okay, so it seems okay, right? So this is 2L max, and we are doing expectation, so expectation being linear, it will go inside. So expectation of fi x star minus, so infimum of fi will be something fixed, right? So okay, so infimum of fi, let us put it there, expectation of infimum of fi. So expectation of fi x star is nothing but the infimum of f, because expectation of fi is f. Okay, so 2L max, and this is in that form, it's infimum of f minus, now expectation of infimum of fi, then here we have to write it in the usual average form, which is 1 by n sum of, so this is in that form, it's 1 by n sum of infimum of fi. Okay, and which is delta f star. Okay, so this is 2L max delta f star. Okay, this is what we were supposed to prove, sigma f star is less than or equal to 2 L max delta f star. The moreover case is very similar. So it says that it's exactly similar, and one has to use lemma. So hint lemma 2.18. That's it. Okay. So because it's mu strongly convex case, so there is a lemma that we did before, and proof is exactly saying it's exactly the same proof, except that instead of lemma we use lemma 2.18 instead of lemma 2.28 that we used here. So that can be left as an exercise. Now moving towards SGD, we have one concept. It's called variance transfer. So need to define variance transfer. So this variance transfer allows to exchange terms like expectation of gradient of Fix whole square with interpolation constants and function values. So that is the use of this. We will see this use in the proof itself. So before that, we have to define these. So this is a variance transfer. So that's the lemma 4.19. So this is variance transfer function noise. So this lemma says that if assumptions such as sum of L max smooth holds, then for all x in Rd, we have expectation of f grad Fix whole squared is less than or equal to 2 L max Fx minus infimum of f plus 2 L max delta star f. Okay, so this variance transfer lemma, and the proof is just 2 lines. So let x be in Rd and x star be in arc mean of f. Then using lemma 2.28 that we wrote, okay, so I will use that lemma again. So using lemma 2.28 we can write, okay, so which is this so this is gradient of Fix squared is less than or equal to 2 L max Fix minus infimum of Fi. So that's the application of the lemma itself. Then since we are Fix star is there, right, and then yeah, infimum of Fi there, but Fix star is not there, but Fix star is needed in the proof, right? So sometimes, as I said, the trick is to bring the term that does not show up somehow. So in this case, I see Fi info of Fi f is not there. Then let us bring Fix star Okay, add and subtract. So so let us do that. So we will add and subtract fi x star. In fact, we will add and subtract 2 L max fi x star. So what I will do is, with this I will just do an equality and then do this in the next step. So this is L max fi x minus fi x star plus 2 L max fi x star minus infimum of fi. So what I have done is that I have added and subtracted 2 L max fi x star. Okay, so and then yeah, looking at this, there is a delta x star f. So it seems like this arrangement will kind of produce this, and this will produce this if I take the expectation maybe. Okay, so we have to see if we can get that, because on the left hand side we are sure that this term is okay, but here we will see, okay, this is fx. So if I take a expectation, okay, then yeah, that's right, it seems to be it seems to be the way that we want. So for instance, if we take expectation here, so expectation of this will give you fx. Okay, the average of fi will give me fx, because fx is indeed the average of fi. Okay, so 1 by n sum of fi. So expectation gives me this, and expectation of this guy also gives me this, because expectation of this will be 1 by n sum of fi at x star will be f x star. So that gives me this, and this guy should be delta f star. That we don't have it now, but the formula itself was this, right? So this was f, expectation of f, and this will be 1 by n sum of infimum of fi. The expectation of this will be 1 by n sum of infimum of fi. So everything seems to be in place. Okay, after taking expectation, it seems to work out here. So this is less than equal to, so we look here, so this is 2 L max. So we can do this extra step like taking expectation. Okay, so and I also bring the expectation inside. So expectation of fi x minus expectation of fi x star plus 2 L max expectation of fi x star minus expectation of infimum of fi. Okay, so this becomes equal to 2 L max, and this is fx. This is fx star, which is also infimum of f, and then plus 2 L max, and then expectation of fi x star is fx star, and minus, because this is infimum of fi, so we have to write it like average, like 1 by n sum of infimum of fi. So it will become like this, 1 by n infimum of fi. I don't know, it was sum of n, I guess. Okay, so and this exactly, the last term was delta f star. Okay, so first term is already there, and this term is delta f star. Okay, so this term is delta f star. Then so this is variance transfer for the function noise. So this is the function noise we did. Now we can do variance transfer for the gradient noise, and with this we have all the tools to just prove the SGD convergence. Okay, so last lemma is lemma 4.20. So variance transfer. So with the SGD proof we will stop. Okay, so SGD proof will take maybe half an hour. Gradient noise. So assumptions are same. But there is additional assumption that we also take sum of convex. So L max smooth plus sum of convex. So assume L max smooth plus and sum of convex. So FIs are convex. Then in that case, this lemma says that expectation of gradient of Fix norm squared is less than equal to 4 L max Fx minus infimum of F plus 2 sigma F star. This proof is also one line, one or like 3 lines, let's say. So let X star be the arg min of F, so that we bring the gradient noise, which is sigma square sigma F star F, and this we recall is a variance of gradient of Fi x whole squared. So now let us write, since here again we are supposed to take expectation of this, so it's natural that we start from the norm of grad Fix and see what it is. So in this case, grad Fix whole squared. Now here we see that on the right hand side we are supposed to produce Fx. So let us say these are after expectation, right? So if I do the reverse engineering, right, so it is supposed to be like Fi, and it is also supposed to be like what will lead to this, right? So these are all after expectation, right? So I am saying what would have been before, right? Fx is coming from expectation of Fi, that's clear, right? So Fx is coming, it is seen as expectation of Fix. Okay. Similarly, this guy could be seen, I can plug in the expectation inside. Okay. Okay. That's how like I do the reverse engineering, right? Maybe while proving. And then sigma star F also is known to us. So I mean sigma star F is already there. It's defined there, right? So I will start with the left hand side, and I mean left hand side is a norm, right? Right hand side we don't have any norm. I mean what we did here is using lemma, right? So should we use the similar lemma, or what difficulty we will face, right? If I use the lemma, then I will have these, right? 2 L max Fix minus infimum of Fi, but how will I get 2 sigma F star? So some trick is needed. Add and subtract. So add and subtract grad Fix star. And also I think we made one mistake, right? Because we want to see, oh, this should be star, right? Like in the sigma, there is a star, right? So what I know for sure is that on the right hand side, I'm supposed to get grad Fix star. Okay. So again, by looking at this kind of hints, we will explicitly try to bring it. So how do I bring it? Like maybe I will add and subtract grad Fix star, so that I will have something coming out for sigma F. The remaining things I still have to see. So that's why they will add and subtract grad Fix star, so that explicitly sigma F star will pop up. Okay. So let us do add and subtract. So the grad Fix minus grad Fix star plus grad Fix star. Okay, and I want grad Fx star, but this will be a square also. Okay, so and From here I will use triangle inequality to get the sigma f star square, that's for sure. Okay. So if we work out a little bit on these terms, then so we have a norm of grad fi x minus grad fi x star plus grad fi x star. Then by triangle inequality, this is less than equal to norm of grad fi x star minus grad fi x star plus norm of grad fi x star. All right, but then we need a square of that. So if we can definitely square it. So if we square it, then this will be whole thing squared. So this is this square plus 2 times of grad fi squared, and then the other term grad fi. But this product term was not needed, right? Or let's see. I mean, this is not needed. I mean, square is not needed. Okay. So we apply triangle inequality and we also square it because everywhere is positive, so we can square it. So we have these mixed terms there, which I may want to get rid of, the last term. So 2ab is a plus b whole square, and 2ab can I write, I mean, what can I say about 2ab, right? So 2ab, so I can say that 2ab is greater than or equal to square plus b square. I mean, less than or greater than or equal to, because a minus b whole square is greater than or equal to 0. So a square plus b square is less than or equal to 2ab. So what I will do is that the last term I will treat it as 2ab and I will substitute it by a square plus b square again. So hence I will have 2 times of these guys. So I can, if I do that, then I will have grad fi x star minus grad fi x star plus 2 times of grad fi x star. Okay. So we got rid of the last term with this. Okay. Okay. So we see that 2 sigma f term is settled. Okay. So 2 sigma f star, we already got that. The last term is indeed that. First one is only yes. Okay. So first one is only grad fi of x. Okay. So everywhere grad fi of x, and this one also grad fi of x, and this one is grad fi of x. And convexity is also given, right? So what do we know from convexity, right? Fy greater than or equal to fx plus grad fxy minus x, right? So it seems like convexity is supposed to be used as well, but there is a norm also, right? Yeah. So we are now thinking about the first term. This we already got 2 sigma f. So that's done. Now we are supposed to show that this guy is less than or equal to 4 L max fx minus infimum of f. And the things we have in hand are L max smooth, and obviously L max smooth is also needed because that's how I will get the L max, right? So let us see how we can settle the first term. Okay, so lemma 4.8. okay, so until now it's fine, and there is a lemma we have proved which is 4.8. okay, that's why we proved these lemmas, right? So the lemma 4.8, it seems to be exactly in this form. It's exactly what we need. So using lemma 4.8, and this lemma, although I have written, but let me go back to the main statement, which was here 4.8. So if you recall lemma 4.8, then it was 1 by L max 2 times is expectation of norm of gradient of fi x minus gradient of fi x star less than equal to fx minus infimum of f. Okay, so we have proved this lemma. We have so from here it's evident, I guess. So first we are supposed to take the expectation, right, and then use this lemma. So taking expectation both sides, so if we take expectation both sides, then we have on the left hand side we started with grad norm grad fi. So this is expectation of norm of grad fi x whole squared, and this came out to be less than equal to 2 times expectation of norm of grad fi x minus grad fi x star norm, and then the second one is already settled. So this is 2 sigma f star. I mean, after taking expectation of that, as we did a little bit ago, little while ago, this expectation of this will be this, right? So we don't have to do anything there. Okay. So and then here for this guy, the one lemma is already sitting there, okay, to be used, and there were squares missing somewhere. So we with this lemma, it's straightforward that we get that for L max fx minus infimum of x. Okay, so this is from here onward, it's still less than equal to, and this is 4 L max fx minus infimum of f and plus 2 sigma f star. Okay, so this was the final lemma, and now we can go with the final SGD proof. So theorem 5.3, and after this we can stop. Okay, so it should not take more than 15-20 minutes maybe. So let's see. So the assumptions are like L smooth and sum of convex. Okay, so assume L max smooth. So the last proof we did, it would be interesting to see what were the assumptions, right? I think our last proof was very general. It was complicated to understand, but we did not have this sum of convex. So it may be that it was, although it was complicated, it was much more general than this case. Okay. So so assume L max smooth and sum of convex. Now consider xt is a sequence generated by a SGD, a sequence generated by the SGD algorithm with step size 0 less than gamma t less than 1 by 2 L max. Okay. By the way, if you are following these notes, then there are errors. Okay. If you are thinking that you will look at, into these notes, but you will get stuck, There I found quite a few error. So it's good that you at least, if you find that you are not understanding from the notes, then watch the video again. Okay, so with this step size, then it follows that expectation of f x bar t minus infimum of f is less than equal to x0 divided by k equals 0 to t minus 1 and gamma k 1 minus okay, and plus k square k equals 0 to t minus 1 divided by sum of gamma k 1 minus 2 gamma k L max. Okay, k equals 0 to t minus 1 and we have sigma star f. So for the stochastic case, this is what we have. And that's why we always have expectation, because we are dealing with a stochastic case. So we can say on average, what do you think? Like your iterates that you have x bar, how far it is from the x star. So then this result says that it's bounded by these terms. Okay, we have to interpret this term. Okay, because there is a step size involved. So what are the good choices of step size that will necessarily make it decrease, right? So one of the things from step size we can conclude is, assuming that we have this, right? We will prove this now, but assuming that everything is okay, then one possibility is that you choose step sizes gamma k such that the sum of the gamma k is infinity. Okay, so from this proves, at least in the stochastic regime, your step sizes should be such that, okay. So for instance, and usually you keep these step sizes between 0 and 1. So can you tell a sequence that takes value between 0 and 1, but then the sum is infinity? What could be that sequence? So gamma k in 0, 1, let's say, you have to produce a sequence of number, and I will make it even more. And the reason, yeah, one thing you can say is like, why not fix any number and that will go to infinity as well, right? So you may not do a decay. You may not do a decay, right? But if you don't do a decay, then this guy will trouble you, because there is one gamma k square sitting on the top. So a good way to run SGD is let gamma k goes to infinity, but gamma square k is something finite. So finite we write like this, less than infinity. So can you give me a sequence that satisfies this, right? The sum of the sequence is infinity, but the sum of the square of the sequence is some finite number. Analysis 1 upon n exactly. So these things are taught a lot to those who do analysis, right? So sequences are 1 by n. Okay, so gamma k you choose, or in this case it's k, so let us say it's k, gamma k is 1 by k. So sum of 1 by k is a divergent sequence, but sum of 1 by k square is a convergent sequence. So if you choose a step size like this, so from the here itself you can say, okay, so sum of k square is your step length is going to settle down because it's convergent. So it will be some finite value, but then these guys gamma k sum that goes here and gamma k sum that goes here, that's going to infinity. So overall you will see these guys are constant, other things are constant, right? So overall this is definitely going to go to 0. Okay. So when designing a step size in stochastic algorithm, you can choose a step size of that form. Okay. Just choosing a constant is not a good idea. That's what this analysis is trying to tell you. Okay. Because if you take a constant, then this indeed goes to infinity, but this also goes to infinity, which will trouble you. So the error will not decrease. Okay. The error will can potentially remain high. So one can do a lot of analysis. So this is the initial hard work you may have to do, but then once you have this, you can play around and design an algorithm which converges faster and so on, depending on these, looking at these parameters. Okay. So let us prove this, and we can do this analysis in more detail later on in the next class. So this is just one sequence that satisfies this. So there will be many sequences like that. So one can choose any one that's favorable there, but so let us. So here I did not say what is x bar. Okay, so x bar is some kind of an average of the iterates that's going on. So where x bar is k equals 0 to t minus 1 and p tk xk with ptk is defined to be like this, is gamma k 1 minus 2 gamma k L max divided by sum of I equals 0 to t minus 1 gamma I 1 minus 2 gamma I L max. So this pk, if I let you kind of prove it on your own, then the sum of these pk's are 1. Okay. So since some of the pk's are 1 and pk values are lying between 0 and 1, essentially you have p is kind of like a distribution here. Okay. So it's as if you are doing some kind of weighted expectation of xk. So you can think of x bar as some weighted average of the xk. Okay. And you can verify that for yourself, that pk sums to 1 and each pk's are between 0 and 1. Okay. So so let us do the proof. Let x star be in argmin of f, then we have, so then we have sigma star f is, the way it's defined is grad f I x star. So this like 4.17 lemma, right? And so at the kth step we will be doing expectation of the ek, right? Because we see only up to the k, right? So let us start by analyzing the behavior of xk minus x star whole squared. Okay. So let us start with this, right? So let us write this. In fact, let us look at xk plus 1 minus x star. Now xk plus 1, since it's a SGD, so xk plus 1 is xk minus gamma k grad f xk, right? So we are going to use that. So we will, in this on the side, we write that xk plus 1 is xk minus gamma k grad f xk. So this is the SGD algorithm. That's how xk plus 1 and sk are related. So we will expand this we will put the value of xk there, and if we put that, and also we will be picking one of the fi, right? So I want to make sure that the notations are, so since it's a stochastic, so we don't take gradient of all, right? We take a gradient of one of the I. Okay, so that's what we have to take in this case. So now let us substitute xk plus 1 like that, right? So notation seems to be fine. So so in this case is xk minus gamma k grad fi xk. So you can say that why did you consider one sample at a time, right? So gradient descent, stochastic gradient descent can happen also with a in a batch, mini batch, right? But we are considering the case where I am taking only one sample loss. Okay, so if you recall, if I have a loss function, then the way we are defining is it's a sum of fi's. Okay, and I corresponds from 1 to m if it's a machine learning thing, right? So then fi's are the loss for each sample. Okay, so one of the SGD algorithm is when I take some k out of m. Okay, so when I'm taking the gradient, when I'm considering the gradient, then I'm considering the gradient, then I'm considering gradient on only some of the samples. So that means that I may take for let us say grad f 2 and then plus grad f 5. Okay, so and then I consider f as an approximation of f2 plus f5. I took second and the fifth sample. So that's one possibility, right? I can have a bunch of samples. So in this case, I have a mini batch, and this mini batch size is mini batch size. In this mini batch, I said I want to choose second and the fifth sample. But here, what we are doing right now, we are doing one at a time. Okay, so here the gradient that we are computing is saying, okay, let us take one at a time. Okay, we may extend this to also mini batch. Okay, there should not be too much of a difficulty, but for the moment, let us say that we pick one loss and put it there. Okay, so we had this xk minus gamma k grad fi xk and then minus x star, and then we are looking at the square of this. So we will do the a plus b whole square, and in this case the a will be xk minus x star will be our a. Okay, and the second term will be b. So squaring this, we have norm of xk minus x star whole square minus 2ab term. So this is like minus 2 gamma k inner product of grad fi xk comma xk minus x star plus gamma k squared gradient of f I xk norm squared. So this is okay, and then we will take expectation that's conditioned on xk. Okay, and then we will use convexity of f and variance transfer lemma. Okay, so there are a couple of things in line. So let us first take the expectation and see what we get. Okay, and then step by step we will use all those arguments. Okay, so taking expectation on both sides. So if we take expectation, then we have expectation of norm of xk plus 1 minus x star is equal to expectation of norm of xk minus x star whole squared plus 2 gamma k expectation of gradient of f xk x star minus xk plus gamma square expectation of, since we are doing expectation at xk at the kth, so it's good to put k here. So k, and then norm of gradient of f of xk whole squared. So I just did it from there. This will be, I guess, fi also. So fi gamma square ek fi xk whole squared. Okay. Okay. Now, what can we do here, right? The last expectation, no, the last expectation sigma k goes with grad fi x star, right? So the last one is not in that form. Anyway, so we may use the convexity then, because in convexity you have that criteria, right, where grad f x y minus x inner product is seen, right? So we can have an bound on that. Okay. So if we recall, the since f is convex, okay, so since since these fi's are convex, we have assumed that it's sum of convex, right? So fi's are convex, so we are going to apply the convexity argument here. So since fi are convex, then we have grad f xk x star minus xk must be less than or equal to fx star minus fxk. Okay, so this is coming from the fact that if you recall convexity, right? So fy greater than or equal to fx plus grad fx y minus x. Okay, so with a proper choice of x, in this case x was taken to be xk and y was taken to be x star. So we have just applied that here. Okay, and it seems to be exactly in the form that we have, so we can immediately bound by that, right? Right. So this will be so we can write that. Okay, so continuing from there, so this will be yeah, so let us start from there. Okay, so this is expectation of k, and is there anything more we can do? So we have this bound. Okay, we will see. So okay, let us do this first. Norm of xk minus x star whole square plus 2 gamma k. So we apply expectation both sides. So this is now expectation of fx star minus fxk and plus gamma square, everything else remains the same. All right, so then our goal is to convexity we have applied. Variance transfer also we can apply, because the last term seems to be the term that deals with the variance. So it seems like the remaining step comes from the variance transfer. Okay, so let us recall the variance transfer. In this case, it's for the gradient or the function noise, right? Yeah, we want to do the gradient one, right? So we recall the variance transfer for the gradient, and in this case we have expectation of norm of fix. So it's we have that term here, and that should be less than equal to 4 L max fix minus infimum of fi plus 2 sigma star fi. So that's where we are going to focus. So if we do that, so let us now focus on this term via variance transfer. So this is via variance transfer. And this is variance transfer is lemma 4.20. So with this, we can write expectation of k norm xk minus x star whole square plus 2 gamma k expectation of fx star minus fxk plus gamma square, and we apply the variance transfer, and that says that this guy must be less than equal to 4 L max. So 4 L max of fix. That's why it's called variance transfer, because the variance is transferred to the function values. Okay, so this is fixk minus infimum of fi and plus 2 sigma star fi. So we applied variance transfer here. Okay, it seems like, I mean, we can go for one more sort of second booster dose of expectation again. So these expectation won't change. That's the nature of expectation, right? Expectation of expectation won't change, right? So we can go for one more. Ideally, what we were supposed to do is do this first, and then we got the expectation, then we got this, and then we got the expectation, then this guy is infimum of fi, right? So I'm missing this fi everywhere. So these terms are matching, right? And we could have taken those common fixi, but with a change of sign in the second term, then it's exactly matches, right? So that's fine. Like we can immediately put one expectation there also. Okay, if you don't get confused, then I can basically I do one more expectation, but nothing changes basically. So I can do an expectation here. Now this expectation term is common, given that I have to flip it here. Okay, otherwise I can take this common. So which one they prefer flipping, right? So that we have it. So the way they write is fxk and then the other one. So this means xk and the other one. Okay, so this means like, okay, but in our case, okay, yeah, so fxk, so basically this one we flip. Okay, so we make it negative here. So let us do it here. Okay, so this we make it negative and we switch it here. So this is fixk. So basically star and k swap. Okay, now these guys are like, sometimes we are writing k down. Ideally, actually it should be up. Oh, but then many places we are writing it down. For gamma it's down, but for k it was up. Yeah, so if we use variance transfer, it is 4 L max. Oh yeah, in variance transfer, actually it's already fx form. Okay, no problem. Then we don't really need expectation. Okay, that's right. Okay, thanks. So then also we are okay. So we then our original plan is fine, that we have expectation for this, but these guys will make it f. So then still we will take it common. Okay, so no problem. So we have fxk minus this, and then the fact that I have expectation here, now these guys will become f f. Okay, fi will change to f. So let us do this one step for clarity. So xk norm of xk minus x star minus 2 gamma k, and this is f. Okay, so I did a minus. Okay, that's already done. The swapping is done. So fxk minus fx star plus gamma square 4L max fxk minus infimum of f plus 2 sigma f squared. Sigma, are we sure that it will be sigma fi or sigma f? Sigma f. Okay, so here also we have little bit of change, so it should be sigma f. Variance is done on fi's. That makes sense because that's kind of like a stochastic term there, but the final term is should be sigma f. Okay, so this is what we have, and with our plan we want to take this common. So let us see what we have. So this is now equal to expectation of norm of xk minus x star minus. So after doing this, yeah, how come 2 gamma k shows up here? Okay. Yeah, 2 gamma k, yeah, that's, but 2 gamma k should not show up with. Okay, they have split the 4 into 2. Okay, that's fine. And these are gamma k, by the way. Okay. Okay, so anyway, like I will do that thing common, and it is okay for the moment. So this is 2 gamma k and 2 gamma k L max minus 1, and then we have fxk minus infimum of f plus 2 gamma k square sigma f star. So this is what we have. Okay, everything is correct. So I should have 4 gamma k L max, 4 gamma k square L max, which I see, and I should have. Okay, why did we have minus, right? There is a minus thing going on here. So there is a problem with the minus sign. Okay, this and we had to do this flipping because we had to take it common. That's where the minus came. So fxk minus infimum of f, fxk minus infimum of f, that's right, and that goes with the minus. Here it will be plus, right? Okay. Then yeah, the way we did this, right? So it seems to be okay. Okay, so okay, we are midway now. We have this now, rearranging and taking expectation. Okay, we will take one more expectation here, that's fine, and we are starting yeah, and then fxk is brought onto the left. In the theorem, if you see, in the end we are supposed to prove expectation of fxk minus infimum. So this is brought to the left and expectation is taken there, and everything else is moved to the right. Okay, so let us do that. Okay, so rearranging and taking expectation. Okay, so if we do that, then we have 2 gamma k 1 minus 2 gamma k L max of expectation of f of xk minus infimum of f and this is less than equal to expectation of norm of xk minus x star squared minus expectation of x k plus 1, right, k plus 1 minus x star whole squared. I hope this will be captured, plus 2 gamma square sigma f star. Okay, so what we have done is did the rearrangement and took expectation. So those expectations which were there or which were constant, they remain the same. So let us see what we did, right? So 2 gamma k, since it went to the left, it became other way. Now it became 1 minus 2 gamma k L max, and expectation went inside f x k minus infimum of f. So this went to the left, and other things went. So this guy went to the right. So this is minus expectation of x k plus 1 minus x star you see as a second term on the right, and then the first term on the right is the same as the first term on the right here, expectation of x k minus x star, and then the other guy is already there, okay, the sigma f term, but that will remain the same, right? Once expectation is computed, that's found, average is found, so that will be a fixed number anyway. After taking expectation, it remains the same. So right, so rearranging, taking expectation, so we have done. Now we will sum from k equals to 0 to t minus 1. So essentially, if you see in the result, in the theorem statement, the final things that you want in the statement, in no intermediate k should remain, right? Because if in the bound on the right hand side you have some k there, then the bound is not really a bound, right? So the k remains a variable there. So that's what you are supposed to do, is that kind of get rid of all the intermediate and go to the end one and x star. So in all the bounds that you do, so do arrangements in a way that you get to see only these terms on the right hand side, okay, which is, I mean, x0, which is the initial guess you always know, so that's a fixed vector, and x star is also known thing, okay, although we are trying to compute, but that will be something fixed. So in the bound you must only see x0 and x star. So that's why we see that there is some kind of telescopic sum. If we do, then intermediate terms kind of will get cancelled, okay, because if you take the expectation common there and so on, so there will be xk minus x star, and there is xk plus 1 minus x star. So you will see a lot of cancellations going until they go to the end boundary of, in this case, will be x0, okay. So that's the plan. So if we do that, so summing over k equals to 0 t minus 1, and using telescopic cancellation, which refers to cancellations going on here. And so if you want, I could have like taking expectation common, because expectation is a linear function, right? So the telescopic sum cancellations is going inside, okay. So if you want, I could have done this. So this is your expectation. So if we sum this, the sum can go inside. Again, expectation is a linear function, so it allows sums to go inside, and then it will do those cancellations that we want, okay. So summing over k equals 0 to t minus 1, and using telescopic cancellation. So what we get is, on the left hand side we get 2 and sum of k equals to 0 to t minus 1 gamma k and 1 minus 2 gamma k L max, and expectation of f xk minus infimum of f. So that's basically the left hand side. We just summed it, k equals to 0 to t minus 1. Okay, so left hand side we are okay, and now let us see the right hand side. So this is less than equal to norm of x0 minus x star whole squared minus expectation of norm of xt minus x star whole squared plus 2 sigma f star sum of gamma k square k equals 1 to t minus 1. Okay, so as you have seen, cancellations have happened. I have missed an expectation here, and the only two terms that now remain, there is still a t term. Okay, we are supposed to get rid of that in the bound. Okay, but we have this lot of cancellation, and now we are left with this. This guy is okay. There is no variable going on here, but we have this xt, which is the last part left, I guess. Okay, so let us see what we can do. So dividing both sides by this guy basically. So we'll divide both sides by this. Okay, in the proof we had only this in the left hand side, so that's what we are trying to do now. We're trying to get rid of these and put everything on the right hand side. So dividing both sides by by 2 sigma I equal 0 to t minus 1 and gamma I 1 minus 2 gamma I and L max. Okay, so and what we are also as I said, we don't want to see any variable on the right hand side, right? But due to our luck, if you see this term is positive, right? So a norm already is a positive, so expectation of a norm will be a positive. Expectation of positive quantity is positive, and it's in negative, right? So this guy is greater than equal to 0. So this tells me that I can safely drop this, and this will still remain an upper bound. Okay, so hence we easily get rid of this troublesome term. Okay, now everything we have is constants. Okay, that's what in bound we need, right? Summation of the, yeah, these are expectations with xk, right? I didn't get exactly what you were trying to say. So you think there is a problem here? Yeah, expectation is being applied here. So now we divide by this. Basically we are doing the cleanup, and we can already see that we are there. Okay, so basically after dividing by this, what we are going to get is this k equals 0 to t minus 1 and expectation of gamma k and 1 minus 2 gamma k L max divided by sum of I equal 0 to t minus 1. So that's the division term we have. Gamma I 1 minus 2 gamma I L max, and we have f x k minus infimum of f. So that's after the division for the left term. Yeah, I mean eventually I decided to keep the expectation outside also, so I changed there, that's fine. And then let us see the right hand side. So this is less than equal to x naught minus x star whole square divided by 2 sigma I equal 0 to t minus 1 gamma I 1 minus 2 gamma I L max plus sigma f star gamma k square k equal 0 to t minus 1 divided by sum of I equal 0 to t minus 1 gamma I 1 minus 2 gamma I L max. Okay. So, we did this division. It looks too many things going on, but it's a simple division we have done. So, as you can see, we are more or less there already. So, we have to like capture this this term in as a pk, right. So, ptk that we defined in the, so this acts like some distribution. Okay. So, we can define pk to be like that, and sum of the ptk, sum of these guys is 1 also. Okay. It can come, right, it's a constant, right. Inner ones are anyway constant. I can make it outside or inside, that's my choice. Gamma k is not necessarily a random variable, right. Gamma k is always something deterministic. I know how to decrease each time. There is no randomness is gamma k. So, overall everything is like a constant. Expectation also can go here, it can also stay here. It does not matter, because this there is no random variable involved here. Random variable is only with xk, because xk is being updated from gradient of xk. Gradient of xk is random, because I am picking samples randomly and computing gradient on them. So, that is why the stochastic gradient is coming from there. The way I am decreasing, it is an algorithm thing. Unless I start choosing gamma k themselves as some random, then I will see. But usually my strategy for gamma k will be some known strategy. So, I do not think I will treat that as a random variable. Okay. So, we will collect this as p. Okay, we will collect this term as ptk. Okay, so finally we define k equals 0 to t minus 1. Finally, define k equals to 0 dot dot t minus 1 as follows. P t comma k is defined to be gamma k 1 minus 2 gamma k L max I equals 0 to t minus 1 gamma I 1 minus 2 gamma I L max. Okay, this is our tk. Now, few things that are that needs to be verified is, obviously it's greater than this, because denominator contains at least the numerator. Okay, and we are we expecting that these guys are less than 1? I hope so. In any case, what we know for sure is that this is greater than this. Okay, denominator is greater than the numerator, so it's less than 1. And and also that ptk are greater than or equal to 0. In fact, sum of ptk is 1. Okay, which makes sense. I mean, this is very clear, right? This is one of the kth term. So, if I sum over the k, this sum over the k for t minus 1, this exactly becomes same as denominator. So, sum of ptk for k equals 1 to t minus 1 is indeed 1 from here, right? And another thing is that ptk are greater than or equal to 0. I hope it is greater than or equal to 0. I believe gamma k is chosen in a way that somehow it balances L max, and it does not, this term does not exceed 1. Okay. So, I believe some condition are there in the theorem itself. So, here it says that note that P T K are greater than equal to 0, and sum of P T K for k equals 1 to t minus 1 or 0 to t minus 1 is indeed 1. So this is exactly the criteria you need for a vector to be a distribution, right? For a vector to be a distribution, it has to take positive values. So this is like a probability distribution, PMF. Okay, so this is like a PMF. Any vector that satisfies this can be seen as a PMF. Okay, so that's what we have it here. So this allows us to treat P T K equals 0 to t minus 1 as if it was a probability. Why do they write vector? I mean, it should be a distribution, right? So indeed, using that f is convex. Okay, so and we are supposed to use Jensen's inequality because here we, so here we want to get rid of this also, right? In the original theorem, we have only fxk minus infimum of f term left. Okay, so we will do that, and we will use the convexity here and Jensen's inequality. Okay, so let us see. So using that f is convex, together with Jensen's inequality, so Jensen's inequality, we have, if you can recall, we did that. So expectation of, so the convex, it applies on the convex, right? So convexity is like f of the line. Okay, so the average of the f is above the f of average, right? So the it's like t plus t of f of x plus 1 minus t of f of y is greater than equal to f of tx plus 1 minus ty. Now then we also told in the class, in the optimization, is like this is like average of the f. So this is like expectation of the f. Okay, of the f is greater than equal to f of the, so let us say this is fx, this is f of the expectation of the x. Okay, average of f must be greater than equal to f of the average. So here here we are supposed to use Jensen's inequality. So if we use that, then so what we will do is, I mean, in the theorem we had expectation of f x bar, right? So I can start from there, let's say, and then along the way we will see how we use the Jensen, right? Because the x bar itself is the average. So the x bar, the way it was defined in the theorem statement, okay, this x bar actually have these terms involved, right? So minus f x star, and this is this must be less than equal to, so I can write this because there will be one additional step, I believe, but let's see. So expectation of gamma k 1 minus 2 gamma k L max divided by sum of I equals 0 to t minus 1 gamma I 1 minus 2 gamma I L max, and then this is f x k minus infimum of f. Okay, so this came from Jensen's inequality. Are you convinced with that? You're convinced, right? So it has been applied on this guy only. Okay, you just keep this separate because this will be a distracting part. Expectation of this minus expectation of this. Okay, and then on this is like expectation of f of the average will be less than equal to expectation of interior. What do you mean by interior? So if I remove the e from there, then they are already less than equal.
Yeah, the E from R is
Yeah, I mean, okay. So this is this inequality is true, you are saying. Yeah, we exactly have that. This pk is with this guy also, right? That's pk f of xk and infim. Okay. Yeah, the other term infim anyway doesn't matter. Agree. So this is like convex combination of these. So basically what we are trying to say is this, the generic form, right? So theta 1 x1 plus theta 2 x2 plus dot 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 plus theta n xn is less than equal to theta 1 f x1 plus theta n f xn. Okay, where sum of the theta I is 1 and theta i's. So this is the more generic thing, and that's what we are trying to say. So f of the less than equal to, and you always forget this, okay, because this is distracting. So you just look at this. So I can write this, okay. So clearly, since f is convex, f x bar t is less than equal to, if you wanted I could have written some here also, I mean, but that should be okay. So k equals to 1 to t minus 1, and I'm tempted to use ptk. Let us use that, ptk and f xk, and yeah, and if you wanted I could have written here ptk xk as well. Okay, so if you wanted we could have also written it like this, sum of ptk xk. Okay, so that's what it's in that form, right? F of sum of theta I xi less than equal to this. In this case we have f of sum of ptk xk, that's defined to be x bar in the theorem. So by convexity this is less than equal to this. Okay, and this guy has no role to play, like this guy, even if it goes there after sum it becomes 1 anyway, right? So I guess this was the, and expectation we can take later. Okay, so we can put expectation. So this I guess there is a last line where fxk, right, so we have this gamma k, this and fxk minus infirm k, and then we had any result on fxk minus infirm k. So here I think we did some result which in terms of, it comes out in terms of norm of x naught minus x square and so on, right? We did this. Oh, the last line, that's already there, right? So the last line is what we need. So this guy is further less than equal to, okay, so if we continue from here, so this guy is further less than equal to that last guy. Okay, so that's equal to this. Okay, and that's the proof of the SGD algorithm, and we will discuss details of the parameters and what role they have to play. Okay. Okay. Thanks.